So today we are tackling a monster of a text. I mean, a real heavyweight.
Oh, yeah. This is not a casual read.
Paul Langackers' The Standard Model and Beyond. And the thing about this book, the second edition, is that it really refuses to coddle you, doesn't it?
Not at all. There's no hand-holding. We're not doing the pop science thing today.
No colorful billiard balls bouncing around on a pool table?
Exactly. We're getting into the heavy gear. If you walk into any high-energy physics department, at CERN, at Fermilab, anywhere,
This is the book you see.
this is the book on the desk. And it's probably got coffee stains on it. It's dog-eared because this isn't a book about what the particles are. It's the manual. It's the grammar that physicists use to actually describe them.
That's a great way to put it, the grammar. And that's really the mission for this deep dive, isn't it?
I think so, yeah.
We want to strip away the metaphors, look at the machinery itself. We're aiming to decode Chapter 1, which is just notation.
The language, yeah.
And then Chapter 2, which is this huge, dense overview of perturbative field theory.
The toolkit.
The toolkit. Yeah. Exactly. Lagrangians, Feynman diagrams, the calculus of, creation and destruction. But before we even get into the math, we have to talk about the elephant in the room.
Or the boson in the room.
The boson in the room, the Higgs.
Always the Higgs.
Because this is the second edition from 2017. The first one came out in 2009.
Right.
That 8-year gap, I mean, you could argue it's one of the most significant periods in modern physics.
Oh, without a doubt. It completely recontextualizes everything. Langacker says as much in the preface. In 2009, the Higgs was this theoretical ghost. We needed it.
Necessity.
A complete necessity to make the math work, to give mass to the W and Z bosons, but we'd never seen it. It was just a variable in our equation.
A placeholder for a discovery we hoped would happen.
And then, the Large Hadron Collider turns on, it starts smashing protons together at these unbelievable energies, and then boom, 2012, they find it.
They find a particle, a spin-zero particle, right around 125 GeV.
Right at 125 giga-electron volts. And that changed everything. The Standard Model was, in a sense, complete. Verified.
It was a triumph, a massive Nobel Prize-winning
A
triumph.
huge triumph. But, and this is where it gets really interesting, Langacker points out something very subtle and, frankly, a little disturbing in the preface to this new edition.
Okay.
It's about that number, 125 GeV. He says it's suspicious.
Suspicious how? You mean the measurement might be...
Well, no, the measurement is rock solid, incredibly precise. The suspicion comes from where that number sits in the grand scheme of things. It's right on a knife edge.
What does that mean, a knife edge?
Well, it's consistent with the Standard Model, barely, but it's dangerously close to a region where the vacuum of our universe could be what's called metastable.
Metastable. That sounds unstable. Like a polite way of saying, it's fine for now, but please don't poke it.
That is exactly what it means. Imagine a ball sitting in a small dip on the side of a huge mountain. It's stable for now, but it's not in the lowest possible valley. Metastability implies that our vacuum state, the ground floor of reality we're all built on, might not be the true lowest energy state.
Just in another lower floor it could fall to.
In theory, yes. It could tunnel through the barrier to a true vacuum state. And if that happened, well, the laws of physics as we know them would be rewritten instantly.
The entire universe would just collapse into a different configuration.
Poof. Gone. Replaced by something else.
Wow. That's a terrifying thought to just, casually drop in a preface.
It is. And for physics, it's also problematic. That mass, 125 GeV, it's also right at the upper limit of what theories like supersymmetry were predicting. It's tantalizingly close.
So it hints that the Standard Model is correct, but at the same time it hints that it's fragile or incomplete.
It feels like a clue that the Standard Model is not the final story, and he lists all the other headaches, too.
Right. Gravity still won't play nice with the other forces. The hierarchy problem.
Why is the weak force so much stronger than gravity? Why is the Higgs scale so different from the Planck scale, where gravity becomes quantum?
We still have no idea what dark matter is, or dark energy.
And maybe the most frustrating thing of all for experimentalists. Silence. We turned on the LHC, we found the Higgs, and then nothing.
Everyone was expecting this whole zoo of new particles to just pop out. Supersymmetry CSY was supposed to be right around the corner.
Just waiting for us.
Yeah.
And it wasn't there. So Langacker's whole perspective in this edition is that the Standard Model is clearly not the ultimate theory. It's too arbitrary, it has too many free parameters, it has too much fine-tuning.
It could be the end of the road.
But, and this is the critical but, it's the effective theory we have. And to go beyond it, you have to master it first. You need to know the rules inside and out before you can spot where they're being broken.
Okay, so let's learn the rules. Section 1 of our deep dive. the language of the universe, notation and units. And right out of the gate, he does the thing that always jars people. He just deletes the constants.
Natural units. It's the first rite of passage for any theorist.
He sets h bar, Planck's constant, and c, the speed of light, equal to 1. Just gone. Is that just to save ink? Is it pure laziness?
It feels like that at first, but it's actually it's a moment of deep philosophical clarity disguised as laziness.
Okay, unpack that.
Think about what our units are. A meter, a second. They're human scales. A meter is some fraction of the Earth's circumference. A second is tied to its rotation. They have nothing to do with the fundamental constants of nature.
They're arbitrary.
Totally arbitrary. By setting c, the speed of light, to 1, we're not just making the algebra cleaner, though it certainly does that. We're making a profound statement.
Which is?
That space and time are the same kind of thing, and that mass and energy are the same thing.
Einstein's famous E equals mc squared?
Exactly. If c is just the number 1, then the equation becomes E equals m.
Mass is energy.
Mass is just a form of congealed energy, and momentum is energy in motion. By getting rid of the conversion factors, we stop thinking in, meters and kilograms, and we start thinking in the one true currency of the universe.
Which is energy.
Energy, and the unit we use is the electron volt, the EV.
So in this system, in these God units, as I've heard them called, everything mass, momentum, even distance and time, it all gets measured in terms of energy.
It all comes back to EV. Mass and energy are measured in EV, and because of h bar being 1, time and distance are measured in inverse EV. It unifies the whole system of measurement.
Let's get a sense of scale here, because he walks through the powers of 10. Where does the physics we know live on this energy ladder?
Okay, so we start really small. At the milli-electron volt scale, MeV, that's 10 to the minus 3, that's where we think neutrino masses live. They're just these tiny, ghostly little things.
Barely there at all.
Barely there. Then you climb up. You hit the mega-electron volt scale, MeV, 10 to the 6. This is the world of nuclear physics. The mass of an electron is about half a MeV.
And a proton?
A proton is much heavier. It's about 938 MeV, which is so close to a billion that we just round it up and call it 1 GeV.
1 giga-electron volt.
Right. And that's a fantastic yardstick. When you see a new particle, you can ask, okay, how many protons is that? It gives you an intuitive feel for its heft.
So using that yardstick, what about the Higgs?
The Higgs boson is about 125 GeV. So in terms of just raw stuff, it's like having 125 protons all mashed together into one fundamental particle.
So the beast.
For an elementary particle, it's an absolute beast. But then you keep climbing the ladder.
Way up.
Way, way up. The scale where we think the strong, weak, and electromagnetic forces might all merge into a single grand unified force, that's around 10 to the 16 GeV.
An absurdly huge number.
And it gets worse. The Planck scale, where gravity finally becomes as strong as the other forces and you need a theory of quantum gravity, that's at 10 to the 19 GeV.
The gap between our heaviest particle, the Higgs at 125, and that Planck scale, it's a desert. There's almost 20 orders of magnitude of nothing that we know of.
It's a vast, empty desert. And that desert is the hierarchy problem I mentioned. Why is there this colossal gap? Why is gravity so ridiculously weak compared to everything else? We have no idea. But using natural units lets us put all these scales on the same plot and talk about them with the same language.
Okay, one last piece of notation before we move on. The geometry of it all. Langacker introduces the 4-vector.
Right. This is pure special relativity. In our normal lives, we think of space and time as separate. A meeting is at 2:00 p.m., that's time. At the coffee shop, that's space.
2 different coordinates.
But relativity weaves them together into a single object, space-time. So a point isn't just XYZ, it's TXYZ. That's a 4-vector.
And to measure distances in this 4-dimensional world, you need a special kind of ruler.
You do. It's called the metric tensor, usually written as G mu nu. And it's not the simple Pythagorean theorem you learned in school.
Where it's all plus signs. A squared plus B squared equals C squared.
Right. In 3D space, distance is just x squared plus I squared plus C squared. But in space-time, the metric he uses is a diagonal matrix of 1, -1, 1, -1, 1.
And those minus signs are everything.
They're the most important symbols in the entire book. That minus sign is what separates time from space. It's what creates the light cone and enforces causality. It ensures that the square of the 4 momentum, p squared, is e squared minus p vector squared, and that has to equal the mass squared.
Let's just pause on that. If it was all plus signs If time was just another spatial dimension.
Then you would have four-dimensional Euclidean space. You could, rotate in the time direction just as easily as you rotate in the space direction. You could turn left into yesterday.
So you could have time travel paradoxes.
All sorts of paradoxes. Those minus signs lock in the causal structure of the universe. They ensure that the past is fixed and the future is open. Cause precedes effect. The math literally encodes the arrow of time into the geometry.
Okay, that's mind-bending. So the rules of the road are baked into the coordinate system itself.
That's a perfect way to put it.
All right, we have our units. We have our space-time grid. Let's start putting things on it. Section 2, the quantum toolkit. This is where we meet the operators, and we had to start with a vacuum. Langackers are very specific. The vacuum is not nothing.
This is such a huge conceptual leap from classical physics. An old-school vacuum is just an empty box, total nothingness.
Right.
But in quantum field theory, the vacuum, which we write as this little kit symbol, 0, is the ground state. It's the state of minimum possible energy.
I think of it like a perfectly still, silent ocean.
Exactly. It's not nothing. It's just quiet. It's the canvas. And to get a particle, you have to disturb it. You have to create a ripple on that ocean.
And the tool for that, the mathematical paintbrush, is the creation operator.
The creation operator, a dagger. It's a beautiful little machine. You take this operator, you apply it to the vacuum state, and pop. A particle with a specific momentum appears out of nowhere. You now have the state P.
And if there's a creator, there must be a destroyer.
Of course. The annihilation operator, just the plain A. If you have a particle in the state P and you hit it with the annihilation operator A, it's gone. Destroyed, it goes back into the quiet vacuum.
But what happens if you try to destroy something that isn't there? If you apply A to the vacuum?
You get 0. Not the vacuum state 0, but the number 0. Null. The math just tells you impossible operation. It collapses.
Okay, so that's the basic toolkit. Create, destroy. But the really quantum part comes from the commutation rules.
This is the heartbeat of quantum mechanics right here. Langacker writes that the commutator, which is a dagger, defined as a times a dagger minus a dagger times a, is not 0.
Which is weird. In normal math, multiplication doesn't care about order. 2 times 3 is the same as 3 times 2.
Exactly. But these are not numbers, they're operators. They are instructions. Think about the instructions: put on your socks and put on your shoes.
The order definitely matters there.
The order absolutely matters. The commutator is a way of measuring how much the order matters. The fact that it's not 0, that it equals 1, tells us that the field isn't a smooth, continuous thing. It's quantized.
It's lumpy.
It's lumpy. It's made of discrete packets, and this leads to his analogy of the harmonic oscillator.
The spring.
The spring. It's the best analogy we have. Imagine that every single point in space is home to a tiny, invisible spring. The vacuum is all the springs at rest, not vibrating.
Okay.
A single particle, like one photon, is one of those springs vibrating at its first energy level. The creation operator is the little mathematical finger that comes in and plucks the spring to make it vibrate.
So a second photon is just plucking the same spring again to make it vibrate at level 2.
That's it. A field is just this infinite mattress of coupled springs, and the particles are just the vibrations in that mattress.
But he says there are 2 different kinds of springs, or at least 2 different sets of rules for plucking them.
Yes. This is the great divide in the particle kingdom: bosons versus fermions.
Bosons being the force carriers, like photons and the Higgs. Fermions being the matter particles, like electrons and quarks.
Right. And the difference is their spin. Bosons have integer spin, like 0 or 1. Fermions have half integer spin, like 12. And that tiny difference in spin completely changes their behavior because it changes their commutation rules.
So for bosons,
Bosons use the standard commutators we just talked about. They are, for lack of a better word, social. They love to be in the same state. You can keep applying the creation operator over and over. You can pile a million photons with the same energy and direction into a laser beam, and they are perfectly happy.
they're gregarious. And fermions.
Fermions are the opposite. They're antisocial. Their operators use something called an anti-commutator, which has a plus sign instead of a minus sign.
So a times a dagger plus a dagger times a.
Right. And that tiny change from a minus to a plus has a monumental consequence. It means if you try to apply the creation operator twice, if you try to create 2 identical fermions in the very same quantum state, the math gives you 0. It's forbidden.
It's impossible. This is the Pauli exclusion principle.
This is the Pauli exclusion principle derived from first principles. You cannot put 2 electrons in the same quantum state at the same time.
And thank goodness for that.
Thank goodness is right. Because fermions can't pile up on top of each other, they are forced to stack. They form shells around an atomic nucleus. That stacking is what gives us the periodic table. It's what gives us chemistry. It's what makes matter solid and stable.
So the entire structure of the universe, the difference between a solid planet and just a soup of light, comes down to a plus sign versus a minus sign in a commutator rule.
That is the power of this grammar. A single symbol dictates the existence of matter as we know it.
Incredible. Okay, there's one more technical piece in this section he mentions. Covariant normalization. Sounds a bit dry.
It sounds bureaucratic, but it's really important for making sure the theory is consistent for everyone.
What does it solve?
It solves the problem of perspective. Imagine you're standing still and I'm flying past you in a spaceship at near the speed of light. Because of Lorentz contraction, you'll see my spaceship as being squished.
Right. Lengths contract at high speeds.
So if we both tried to measure the number of particles per cubic meter inside my ship, we'd get different answers because my meter is shorter than your meter. We would disagree on the particle density.
Which would mean the laws of physics depend on how fast you're going. It's a huge problem.
It's a theory breaker. So covariant normalization fixes this. We adjust the definition of our quantum state. Instead of just normalizing by volume, we sneak in a factor of 2e, twice the particle's energy.
And why does that help?
Because energy also changes with speed, and just the right way to cancel out the change in volume.
Yeah.
By adding this energy factor, we both end up calculating the exact same number of particles, the exact same physics, no matter how fast we're moving relative to each other.
It makes the theory democratic. Every observer gets the same result.
It makes it Lorentz invariant. It's a crucial piece of internal consistency.
All right, so we have our particles and our rules for counting them. Now we need the laws that govern how they behave. Section 3. The Lagrangian. Langacker calls this the central density function. I always found this approach so much more elegant than Newton's EFMA.
Oh, it's vastly more elegant. Newton's laws are all about vectors, forces, and accelerations, pushing and pulling. You have to keep track of all these arrows and directions.
It gets complicated quickly.
The Lagrangian, written as a script L, is a scalar. It's just a number. And it's defined in its simplest form as the kinetic energy minus the potential energy, T minus V.
And the whole universe operates based on this one simple subtraction.
The universe operates on the principle of least action. The idea is that a particle moving from point A to point B will explore all possible paths, and the path it actually takes is the one that minimizes the action.
And the action S is just the sum of the Lagrangian over the entire path through space and time.
Right. It's like nature is fundamentally lazy or, efficient. It always finds the most economical path. And if you use calculus to find that path of minimum action, using what are called the Euler-Lagrange equations, the equations of motion just pop out automatically.
So our job as physicists isn't to figure out the forces. It's just to write down the correct Lagrangian for the universe.
That's the holy grail. If you have the ultimate Lagrangian, you can derive all of physics from it just by turning the mathematical crank.
So Langacker gives us a toy model to play with, the Hermitian scalar field.
This is the Hello World program of quantum field theory. It's the simplest possible interacting field you can write down. Hermitian just means the particle is its own antiparticle, like a neutral pion. Scalar means it has spin 0.
And the Lagrangian for this field has a few parts.
3 main parts. You have a kinetic term, which is about the field changing or moving through space. You have a mass term, which is the energy of the field just existing. And then you have the interesting part, the interaction term, V sub I.
Because without interactions, particles would just fly past each other in the dark forever. Nothing would ever happen.
Exactly. A free field theory is the most boring theory imaginable. All the interesting physics, all the collisions, decays, all of creation is in that interaction potential.
And Langacker shows us what those terms look like. He writes things like a phi cubed term and a phi to the 4th term.
Right.
Let's decode those.
Yeah.
What does a phi cubed term in the math mean for the actual particles?
Physically, it represents a point in space-time where 3 particle lines meet. It's a vertex. So it could be one particle coming along and suddenly decaying into 2 other particles. Or it could be 2 particles coming in, annihilating, and forming a single new particle.
So 1 to 2 or 2 to 1, and phi to the 4th.
That's a vertex where 4 lines meet. The most common example is 2 particles come in, they interact at a point, and 2 particles go out. That's scattering. That's what we do all day at the LHC. We smash 2 things together to see what 4 things come out.
Now, this is where he draws a really deep insight that I want to spend a moment on. He mentions that you could, in principle, write down phi to the 5th term or phi to the 6th and so on.
You could, mathematically.
But he says we generally just ignore them. Why? If the math allows it, Why doesn't nature seem to use them?
This gets us to one of the deepest ideas in modern physics, the concept of renormalizability and effective field theories. It all comes down to the units.
Okay.
In our four-dimensional spacetime, the phi to the fourth term has a coupling constant, lambda, which is dimensionless. It's just a pure number. But if you try to write down a phi to the fifth term to make the units work out, you have to give it a coefficient that has units of inverse mass, like 1 over m.
Where m is some really big mass scale.
Exactly. Maybe it's the Planck mass, or the mass of some new super heavy particle we've never discovered. Now, at the low energies where we live and do our experiments, that 1 over m factor is a tiny, tiny, tiny number.
So it suppresses that interaction.
It makes it incredibly weak. So phi to the fifth interactions might be happening all around us, but they're so rare and feeble that they are effectively invisible. We can safely ignore them in our calculations.
But what if we built a collider that could reach energies close to that m scale?
Then you're in trouble. As your interaction energy gets close to m, that term is no longer suppressed. In fact, it blows up. The theory stops making sense. It gives you infinite probabilities. It diverges.
So the theory has a built-in expiry date.
That's the modern view. This is why Langacker calls the standard model an effective field theory. It's a brilliant, stunningly accurate, low-energy approximation of reality.
It's not the truth with a capital T. It's the truth that works up to, say, a few TeV.
That's it perfectly. It's like looking at a pixelated digital image from really far away. It looks smooth and perfect. But if we could build a powerful enough microscope, a collider the size of the solar system, we would eventually see the pixels, would see these higher order phi to the fifth terms start to matter.
That completely changes how you think about the standard model. It's our best ever description of the world, but it knows it's incomplete.
It has its own incompleteness theorem built right into the math.
Okay, so we've written down our Lagrangian, but it's just a dense line of algebra. Section 4 is about how we visualize it, how we turn it into something intuitive. Enter Richard Feynman.
Feynman, the absolute genius, he realized you could just draw the equations. He turned all this terrifying calculus into what looked like simple cartoons. But they're not cartoons. They are a rigorous one-to-one mapping of the math.
The Feynman rules. So every piece of the Lagrangian corresponds to a piece of a diagram.
Every single piece.
Let's build one. We need lines to represent the particles.
Those are the propagators. A line in a Feynman diagram represents a particle traveling from one point in space-time to another. And Langacker gives us the formula for that propagator. It's r over k squared minus m squared.
Okay, I have to stop you on that denominator. K squared minus m squared. We just said that for any real particle, its 4 momentum squared, k squared, has to equal its mass squared, m squared. That's what it means to be a physical particle.
Right, that's the rule. E squared minus p squared equals m squared.
But if k squared equals m squared, then the denominator is 0. And dividing by 0 gives you infinity. The formula explodes.
Which tells you something absolutely profound.
What's that?
The particles represented by these internal lines in the diagrams, they cannot be real particles. They're what we call virtual particles. They are off-shell.
Off-shell, as in not on the mass shell defined by Einstein's equation.
Exactly. They are allowed for a fleeting moment to violate the laws of energy and mass conservation thanks to the Heisenberg uncertainty principle. They exist on borrowed time and borrowed energy. They are mathematical ghosts that exist just long enough to mediate a force between two real particles before vanishing.
So the things carrying the forces are literally rule breakers?
They are. The only particles that have to obey the rules are the external ones. The particles that come in from the accelerator and the ones that fly out and hit your detector. Those are on shell. The virtual ones in the middle are the Wild West.
Okay, so we have lines for propagators. What about the interaction terms, the phi to the fourth stuff?
That becomes a vertex. It's the knot where the lines meet. If your Lagrangian has a phi to the fourth term with the strength or coupling of lambda, then the Feynman rule is every time you draw a point where 4 lines meet, you have to include a factor of EEE times lambda in your calculation.
It's literally a translation key. Picture equals math.
A perfect translation key. And there's one more rule at the vertex. Conservation of momentum. Whatever total 4 momentum flows into the vertex must be the same as what flows out. You can't create or destroy energy or momentum in an interaction.
Langacker shows this with the classic example. 2-to-2 scattering. 2 particles come in, 2 go out. But he breaks it down into different channels, ST and U. These always confuse me. Can we visualize them?
They confuse everyone at first, but they're just different ways the collision can happen geometrically. Think of this 6 channel first. This is a merger. or annihilation. Two particles come in, they smash together, and they annihilate, forming one single temporary virtual particle.
A bottleneck.
A total bottleneck.
Yeah.
Then that one intermediate particle decays back into the two outgoing particles. And this channel is incredibly important.
Why?
Because if the total energy of the incoming particles just happens to exactly match the mass of that intermediate virtual particle, you hit a resonance, the probability of the interaction skyrockets.
You get a huge spike in your data at that energy.
A huge spike. That is exactly how we discovered the Higgs. We saw a massive six-channel resonance when the collision energy was 125 GeV. It told us we were creating a new particle with that mass.
Okay, so 6-channel is a direct hit and merger. What's the T-channel?
The T-channel is more of a glancing blow, a pass. The two incoming particles don't actually annihilate each other. They fly past each other, and as they do, they exchange a virtual particle.
Like two skaters throwing a medicine ball back and forth.
That's the classic analogy. They never touch, but the exchange of the ball pushes them apart. That exchange particle is the force carrier. This is how, for example, two electrons repel each other. They're exchanging virtual photons in the T-channel.
So S is a collision, it is a deflection. What on earth is the U-channel?
The U-channel is a purely quantum mechanical weirdness. It's like the T-channel, but it accounts for the fact that fundamental particles are indistinguishable.
Okay.
If two identical electrons scatter, you can't tell which one came out on the left and which one on the right. Did electron 1 go left and electron 2 go right? Or did they swap places? The U-channel is the diagram that represents that swapped possibility. You have to add both the T and the U-channel diagrams together to get the right answer.
Because you have to account for all the possibilities that you can't distinguish between.
Quantum mechanics forces you to sum over all indistinguishable histories.
This geometry leads us straight into section 5. Kinematics. We call these variables, S, T, and U, Mandelstam variables. Why invent new letters? Why not just talk about energy and scattering angles?
Because of our old friend Lorentz invariance, if you and I are watching a collision from different moving reference frames, we will disagree on the energies of the individual particles. We will disagree on the scattering angles. Those numbers are subjective.
They depend on the observer.
Right. But the Mandelstam variables are clever combinations of energy and momentum that are invariant. They are the same for every single observer in the universe. Charge, for example, is the square of the total center of mass energy of the collision. That number is an objective fact about the event.
So using them purges the subjectivity from the calculation.
It makes the math cleaner, and it focuses on the fundamental observer-independent properties of the interaction.
Even so, Langacker points out that you still have to choose a frame of reference to actually do the calculation.
Yes, you have to pick a convenient point of view. The most common one for theorists is the center of mass, CM frame.
The fair frame.
The fair frame. It's the one where the total momentum of the incoming particles is zero. They come at each other head-on with equal and opposite momentum. It's beautiful and symmetric, which makes the algebra much, much easier.
But that's not what an experiment always looks like.
Not at all. Many experiments use a fixed target. You have a beam of protons, and you fire it at a block of stationary liquid hydrogen. That's the laboratory frame.
And the math is uglier there.
Much uglier because everything is moving in one direction. It's asymmetric, but it matches the reality of the hardware, so you have to be able to do calculations in that frame too.
And then there's this weird one, the bright frame, which he calls the brick wall frame.
Yeah, that's a very specialized, clever choice of coordinates. It's mostly used for looking inside things, like probing the structure of a proton. You choose your frame so that it looks like the particle you're firing, say a virtual photon, carries no energy, only momentum. It hits the proton like it's hitting a brick wall and bounces straight back.
And that simplifies the math for what you're trying to calculate.
It simplifies the momentum transfer calculation enormously. It's a mathematical trick. A huge part of being a theoretical physicist is not about being good at doing hard integrals. It's about being clever enough to find the reference frame where the integral is easy.
It's all about choosing the right perspective.
90% of the job.
Okay, so we've got the variables, we've got the diagrams. Section 6, measuring reality. How do we connect this abstract math to a number that a detector can actually measure? We need to talk about cross-sections.
This is the bridge from theory to experiment. The Feynman diagram calculation gives you a number called the scattering amplitude, m sub phi. It's usually a complex number.
And detectors don't measure complex numbers. They just register a click.
Right. So the first step is to get a real number that's related to probability. We do that by taking the squared modulus of the amplitude, m phi squared.
So that gives us the raw probability of the interaction.
Proportional to it, yes. But to get the cross-section, which has units of area and you can think of as the effective target size of the particle, you need to account for two other things.
He mentions flux and phase space.
Right. The flux is the how hard are you trying factor. It's about the incoming beams. How many particles are you firing per second per unit area? You have to divide your result by the flux so that your answer is a fundamental property of the particle, not just a property of how powerful your accelerator is.
You're normalizing for the intensity of the beam.
And phase space. Phase space is about the outgoing particles. It's the volume of possibilities. After the collision, how many different ways can the outgoing particles fly away while still conserving energy and momentum?
It's like the size of the dance floor they have to move on.
That is a perfect analogy. If you're trying to create very heavy particles and you only have just enough energy to do it, the phase space is tiny. The dance floor is a closet. The reaction is kinematically suppressed.
It doesn't matter how strong the interaction is. There's just nowhere for the final products to go.
Exactly. But if you have tons of excess energy, the phase space is huge, the dance floor is a ballroom, and the reaction becomes much more likely. So the final formula is roughly cross-section equals amplitude squared times phase space divided by flux.
Okay, that makes sense. He also briefly mentions decay rates, gamma.
This is for a single unstable particle just falling apart on its own, like a Higgs boson decaying into 2 photons. The calculation is similar, but the main constraint is simpler.
Mass conservation.
The mass of the parent particle must be greater than the sum of the masses of the daughter particles. You can't decay into something heavier than you are.
Seems obvious, but it's a fundamental rule that forbids a lot of things from happening.
It does, and he touches on the optical theorem here, which is a really deep and beautiful consistency check. It's a consequence of unitarity.
Which basically means probability has to be conserved. The sum of all possible outcomes of an interaction must be 100%.
Right. The particle has to do something. The theorem provides a surprising link. It says that the imaginary part of the amplitude for a particle to scatter forward, to go straight without deflecting, is directly proportional to the total cross-section for it to do anything else at all.
Wow.
It's a check that makes sure your theory isn't losing probability somewhere. If your theory violates the optical theorem, it's fundamentally broken.
Okay, we're getting into the really deep water now. Section 7. Loops.
Yes. Welcome to the nightmare and the glory of quantum field theory.
So far, we've just talked about tree-level diagrams, simple lines and branches. But what happens when a particle emits a virtual particle and then reabsorbs it itself? You get a loop in the diagram.
A bubble. And the problem with that bubble is the momentum flowing through it. In a tree diagram, momentum conservation at each vertex locks down the momentum in every single internal line. It's a solvable puzzle.
But in a loop.
In a loop, the momentum is unconstrained. The virtual particle inside the loop can have any momentum it wants, from 0 all the way up to infinity, as long as it all balances out in the end.
So to get the right answer, you have to sum over all those infinite possibilities.
You have to integrate over all possible loop momenta from k equals 0 to k equals infinity.
And whenever you integrate up to infinity.
You get infinity, the calculation just breaks. It spits out a meaningless, infinite answer.
This was the crisis that almost killed quantum field theory in the 1940s. So how do we fix it? Renormalization.
It sounds like a dirty trick. It really does. But it's actually one of the most profound insights we've ever had. The key idea is to recognize that the parameters you wrote down in your original Lagrangian, the bare mass and the bare charge, are not the quantities you actually measure in an experiment.
They're just abstract symbols in the math.
Right. What you measure in the lab is the physical mass, the physical charge, which includes all these complicated loop effects from the particle interacting with its own virtual cloud.
So what do you do with the infinity? You perform a bit of mathematical magic. You say, okay, this integral is infinite. I'm going to split it into 2 parts. You absorb the infinite part into the definition of the bare mass, effectively hiding it.
You sweep the infinity under the rug of your definition.
You sweep it into the difference between the unobservable bare parameter and the observable physical parameter. And the miracle is, once you do this for the mass and the charge, all the other infinities that pop up in other calculations magically cancel each other out.
And it actually works.
It works so well that in quantum electrodynamics, the predictions match experiments to 12 decimal places. It's the most successful and precise cheat in the history of science. It tells us that even though our theory has these infinities, it's still internally consistent and predictive.
Incredible. Okay, Langacker finishes this section by upgrading our toy model. We move from a simple Hermitian field to a complex scalar field. This is a crucial step. A real Hermitian field describes a particle that is its own antiparticle. A complex field is one where the particle and antiparticle are distinct. Think of the positively charged pion, pi plus, and the negatively charged pion, pi minus.
And what does that change in the formalism?
It means we now have arrows on our Feynman diagrams.
To track the flow of charge.
Exactly, and this leads to Feynman's brilliant and brain-melting convention. An antiparticle moving forward in time is mathematically identical to a regular particle moving backward in time.
So when I see an arrow on an internal line pointing against the flow of time,
It's just an elegant way of drawing an antiparticle moving with the flow of time. It makes the rules for conservation incredibly simple. At every vertex, you just have to make sure the arrows flow continuously, charge is conserved. You can't have two arrows crashing head-on or two arrows flying away from each other.
the current has to be continuous. Which brings us perfectly to the grand finale,
Right.
Section 8, Symmetry and Conservation. Where does that rule, that conservation of charge, actually come from?
This is, for my money, the most beautiful idea in all of theoretical physics. Noether's theorem.
From the brilliant mathematician Emmy Noether.
An absolute giant. In 1915, she proved a staggering connection. Conservation laws are not just arbitrary rules. Every conservation law is a direct consequence of continuous symmetry in the laws of physics.
Okay, let's break that down. What's the symmetry responsible for conserving electric charge? He calls it U1 phase symmetry.
Okay, look at the Lagrangian for our new complex field. It has terms that look like phi dagger times phi. Now, phi is a complex field. It has a magnitude and a phase, like a little arrow on a clock face.
Right.
What happens if I rotate the phase of that little arrow everywhere in the universe at once? I multiply phi by e to the I theta. And to keep things balanced, I multiply phi dagger by e to the minus I theta. What happens to the product phi dagger phi?
The e to the I theta and e to the minus I theta multiply to 1. They cancel out. The product doesn't change at all.
It stays exactly the same. The Lagrangian is invariant under this global phase rotation. The physics literally does not care what angle that little clock hand is pointing to. That is a continuous symmetry.
And Noether's theorem says,
Noether's theorem proves that for any such continuous symmetry in your action, there must exist a corresponding conserved current and a conserved charge.
and in this case, that conserved charge is.
Electric charge.
So the reason charge is conserved in the universe is because the fundamental equations of nature have this deep, abstract, rotational symmetry baked into them.
Yes, it's not a rule. It's a consequence of the geometry of the theory. And it's true for all the big conservation laws. Conservation of energy comes from the fact that the laws of physics are symmetric in time. They're the same today as they were yesterday.
And conservation of momentum.
Comes from symmetry in space. The laws are the same here as they are on Mars, and conservation of charge comes from this internal, complex phase symmetry.
That is just breathtaking. It reframes all of physics. It's not a list of laws, it's a list of symmetries.
And that's the foundation of the entire Standard Model. It is a gauge theory. We build the theory by demanding that certain symmetries hold true. The forces of nature, electromagnetism, the weak and strong forces, they emerge as necessary additions to the theory to maintain those symmetries.
So we've done it. We've gone all the way from defining what a unit of energy is to deriving the conservation of electric charge from pure geometry. Why? Why does Langacker drag us through this dense mathematical jungle?
Because you can't possibly understand the rest of the book, the beyond part, if you don't speak this language. This perturbative field theory is the essential toolkit. We're about to use it to tackle the strong force QCD, which is a beautiful mess. We're going to face the electroweak theory, where symmetries are subtly broken.
And we're going to face the search for things like supersymmetry.
The search for the things that should be there, according to our ideas of symmetry and naturalness, but so far aren't.
And that brings us all the way back to where we started, that metastable vacuum.
Exactly. Langacker leaves us with this profound sense of unease. The mathematical structure we've just outlined is unbelievably beautiful. The symmetries are perfect. But the actual numbers that nature chose, the 125 GeV mass of the Higgs, the tiny mass of the neutrinos, the value of the cosmological constant, they all look a bit weird. They suggest this beautiful structure might be an accident, or that it's fragile.
Like we've built this magnificent, perfect castle, but we're slowly realizing the ground it's built on might not be stable.
Or it's just the tip of a much larger, much stranger iceberg. The tools we've just spent this time learning, The Lagrangians, the Feynman diagrams, renormalization, these are the tools the next generation will have to use to dig deeper and find out what's really holding this castle up.
The beyond in the Standard Model and beyond.
That's the whole game.
That is a fantastic and slightly unsettling place to leave it. We've decoded the grammar, we have stared into the quantum loops, and we've seen the deep beauty of symmetry. A huge thank you for guiding us through the density of these first 2 chapters.
My pleasure. It is a steep climb, but the view from the top is absolutely worth it.
And to you, the listener. Next time you see one of those little Feynman diagrams, remember what it is. It's not just a doodle. It is an equation, it's a story, and it's a precise calculation of a tiny piece of reality itself. Go dig into the sources, check the math, and until next time, keep diving deep.